I'm going to talk about two types of waves referred to as transverse waves and longitudinal waves. I'm also going to talk about sound and light waves. Okay? Now, imagine that you had a long spring. Let me make a picture of a spring. All right. Now, let's fasten one end, perhaps to a fence post. Okay, so I'll make a picture of a fence post here on the end. And so we'll tie it down somehow. Okay. Now, there are various ways that you can vibrate this spring, isn't there? So, one way that you can vibrate the string is to grab the other end of the left end and move it up and down. Okay, if you do that, you will make a wave shaped something like the purple curve moving down the spring. Right? Now, that's not the only way that you can vibrate the spring. What if you, instead of moving it up and down, you pushed the spring towards in the direction of the fence post? Okay? What would that do? Can you see that that would compress the spring, and that compression would move down the spring? Okay? Now, you wouldn't compress the entire spring at the same time. You would compress a portion of it, but the portion that was compressed would move to the right in time. All right? Now, when you make the spring move, when you make the pieces of the spring move in a direction perpendicular to the direction of travel of the wave, like with respect to the purple curve, that's called a transverse wave. Okay? Now, when you make the vibrations in the direction of the wave, okay, that's referred to as a longitudinal wave. All right? Now, let me repeat. What's different is how the direction of the vibrations of each piece of the medium is moving with respect to the direction of the wave. All right? For transverse, they're perpendicular. For longitudinal, they're parallel. They're in the same direction. All right. Now, let me give you some examples of transverse and longitudinal waves. Okay? So, an example of a transverse wave is a light wave. All right. Now, light might seem a little bit mysterious. What is vibrating in a light wave is, in a sense, the space itself is being altered. Okay. You'll hear terms like the electric and magnetic field. All right. But whatever is vibrating, we won't go into that right now, but the property, the parameter, the whatever you want to call it that's vibrating, it's perpendicular to the direction of travel of the light wave. Okay? On the other hand, sound waves are longitudinal. All right? Right now that I am talking, let's think about what the air is doing in front of my mouth. So what I'm doing is I'm pushing the air in front of my mouth. And so it's compressing the air in front of my mouth, which is pushing the air further in front, okay? And so that you have a compression wave. But the motion of the air molecules, atoms, particles, whatever, is in the direction of travel of the sound wave away from my mouth. Can you see that that's a lot like when you push the spring in the direction of the fence post? All right, so that's a longitudinal wave. Now, let me give you some more details about sound and light waves. All right. So, at sea level, all right, and this varies with temperature and pressure and altitude, but at sea level for typical temperatures around 70 degrees Fahrenheit or 20 degrees Celsius, the velocity of sound is about 340 meters per second. All right. On the other hand, watch this. The velocity of light is 3 times 10 to the 8 meters per second. Okay? So, in other words, 30 million meters per second. Okay? If you're more familiar with miles per hour, the velocity of light is roughly 2/3 of a billion miles per hour. Okay? So, the velocity of light is unbelievably large. All right? In fact, when astronauts were landing on the moon, they could communicate with Earth. The engineers in Houston could say something and it would travel at the speed of light, okay, and it would take roughly a second for the astronauts near the moon to hear it, okay? Whereas sound can maybe travel, well, we know how much it can travel in 1 second, right? About 340 meters, all right? So, right, a couple of football fields compared to traveling to the moon, all right? Now, another example that shows you the vast difference between these velocities is that when you're near a lightning storm, all right, you will see the lightning before you hear the thunder, right? Again, that's because light is traveling so much faster than sound, okay? If you go to a baseball game and you have seats that are far away from home plate, you might notice that this strange effect happens. The batter will seemingly hit the ball and start running towards first base, and then you'll hear him hit the ball while he's running towards first base. Okay, again, that's because the light is reaching your eyes so much faster than the sound of the bat hitting the ball. Okay? Now, if that was not interesting enough, I have some more facts about light waves. So, your eyes can see certain frequencies of light waves, okay? Your eye registers different frequencies by, your brain turns different frequencies into different colors. Or I don't know if you knew that, but different colors imply different frequencies of light waves and different wavelengths, all right? For example, red light is with respect to a wavelength of about 700 nanometers. All right? Blue light is with respect to a wavelength of 400 nanometers. They both travel at the same velocity, but they have different wavelengths and frequencies. All right? Now, there are even frequencies that your eye is not able to see. All right? You can think of them kind of as invisible colors. If the wavelength gets too small, then a little bit smaller, if it gets too small, a little bit smaller than blue, then that's what we call ultraviolet light. All right, ultra means above, so it's above violet. Violet being the color that has the smallest wavelength that your eye can see. Okay? Then if you make the frequency even higher or the wavelength even smaller than ultraviolet light, that's how you form what are referred to as X-rays. Okay? And then even shorter wavelengths or higher frequencies in X-rays, you have what are called gamma rays. Gamma ray light waves. Okay? You get gamma ray light waves, like for example when something dramatic happens like two black holes collide. Okay, those are very high energy waves. Okay, what about very large wavelength waves? Okay, if you have a wavelength bigger than the wavelength of red light, so big that you can't see it, if it's a little bit bigger, you have what's referred to as infrared light waves. Okay, infra means below. All right, so the frequency is less than the frequency of red light. That's why it's called that. And then if you have an even smaller frequency or an even bigger wavelength than infrared light, you have what are called microwaves. Okay, and these are well suited to heat up the water in food. That's why we have microwave ovens. And then the largest wavelength light waves are radio waves. So if your eyes were able to see radio waves, every time you drive by a radio tower, it would be like a light bulb, right? You'd see light streaming from it. Okay? Now, I would like you to note the wavelengths of red and blue light, and I'd like you to do an exercise for me. I'd like you to calculate the period and frequency of red and blue light. All right, so here's what I want. Now remember, I gave you the velocity of light, and let me reiterate that all colors, in fact even the invisible colors, all the infrared light, microwave light, all of that travels at the same speed of light of 3 × 10⁸ meters per second. All right, so go ahead and pause the video and find these parameters if you can. All right, so I'll go ahead and calculate those now as well. So the velocity of light, by the way, the velocity of light is often denoted by c, and our wave formula says that that's equal to wavelength over t, where t is the period, or wavelength times the frequency. All right, so the frequency is the wavelength divided by the speed of light. Okay, so for red we have 700 nanometers, 700 × 10⁻⁹, divided by 3 × 10⁸. So I've converted the units of wavelength to meters and the units of speed of light to meters per second, or I've denoted them in SI units. Okay, so that gives 2.3 × 10⁻15 seconds. That's a very small number. So obviously light, the associated vibrations of light for visible light is very fast. Okay, and then for blue, so again lambda over c, so 400 × 10⁻⁹ divided by 3 × 10⁸. So it'll be a little smaller. So for that we will get 1.3 times 10 to the minus 15 seconds. All right, and then for the frequency, we'll just invert what we got for the period, and so that is for red 4.3 times 10 to the 14 hertz. And then finally for blue, the inverse of the period for blue light, and that's equal to 7.5 times 10 to the 14 hertz. Okay, and I hope that that's what you got.